Okay, let's go. So, right, where did we stop last time? Let's review. So we were thinking about which integers are represented by this norm form, which is the norm of x plus omega y, right? Which n are represented. Right? That ring a bell? And we observed that no numbers, did we do this already? Lemma, if n is congruent to 2 mod 3, then n is not represented, cannot be written in this way. We proved this last time. The proof was look mod 3 at all values of this as x and y range, and you never get the value 2. Can I get a thumbs up if that rings a bell? Any thumbs down? Any questions about that? Okay, looks good. So then the theorem that we're working up to, let's start with primes. If P is a prime that's congruent to 1 mod 3 is prime, then there do exist integers x and y such that P is equal to x squared minus xy plus y squared. Okay, so this is pretty similar to our theorem about sums of two squares, except instead of checking if primes are 1 mod 4, we're checking if primes are 1 mod 3 in this case. Okay, and it's going to be a very similar algorithm. Not only do they exist, not only do x and y exist, but they can be found efficiently. They can be determined efficiently. Okay, same as what happened with sums of two squares. So how do you do this? So step 1. If you remember what step 1 was in the other proof, when we had sums of two squares, step 1 was to find something that behaves like I. Find a fourth root of I. You kind of remember that? Karen, I never got to your question last time. You asked, how did we do it for sums of two squares? And I said we'd review, and we ran out of time to do that review. But we're kind of reviewing it as we are doing it for this novel setting. So step 1 is find a number z that's not 1, but its cube is 1 mod p. Mod p. And how do we do this? Anybody remember? A couple of people are typing. Right. Do you guys remember? Dipendra is reminding us. So, how to do this? How to find z? Well, you look at a to the p minus 1 over 3. And if that happens not to be 1, so if this thing is not 1, then z equals a to the p minus 1 over 3, satisfies z cubed. Well, z was a to the p minus 1 over 3, so this is a to the p minus 1 over 3 cubed, which of course is a to the p minus 1, and now Fermat's little theorem tells us that's 1 mod p. Okay? Can I get a thumbs up if that makes sense? Any questions on that? Okay. Okay, looks good. So, let's see. I don't want to go too far into this argument, but let me just let's prove that this will happen by kind of observation. So the two equations we're thinking about are z cubed is congruent to 1. So in general, if you have a cubic polynomial, you kind of think maybe there should be 3 roots. Maybe there should be 3 roots. 3 solutions. Let's look at the polynomial z cubed minus 1. I mean, equivalently, z cubed minus 1 equals 0. So there should be 3 roots of this polynomial, z cubed minus 1. Okay? And did you do the exercise? Last time we looked at tables of a to the p minus 1 over 3 mod p as a ranges mod p. Did anyone do those exercises? Well, let's do them now, kind of quickly. So let's see. Can I open Mathematica? And can I share the screen? Settings, make full screen. How do I share the screen? Is this it? Restore presentation? Restore presentation, can you see me now? No. I didn't test this. What's that? Add. Take presenter. Right. Let me. I see. I have to take presenter, and then I can share the screen with you. Let's go back to this. Okay. Can you guys see anything? Can you see this blank screen? Can you give me a thumbs up if you see a blank screen? Okay. So give me somebody give me a large prime. What's a sizable prime? 43. Okay, 43. Good. So P equals 43. Is that actually a prime? Yes, it is. Is that, I shouldn't have, let's leave that there. Is that prime mod 3 equal to 1? Yes, it's 1 mod 3. Okay, 97 is another good one. We'll come back to 97. Well, all right. So let's make a table of A against A raised to the p minus 1 over 3. So that's the power mod function, because we're going to do this efficiently. So A raised to the power p minus 1 over 3 mod p. That's what this is doing, as A ranges from 1 to p minus 1. And there it is. Let's see if we can see it a little bit nicer. I think I do transpose and then matrix form. So here's this table out to 43. Let's make this slightly smaller. Can you guys see this? So 1 raised to the, what's p, okay, so let's write some of this down. Can you also still see the paper? Yes, great. You can also still see the paper. So example, p equals, what did we do? 43. And here was a table of A versus, so p minus 1 over 3, p minus 1 is 42. 42 divided by 3 is, a little help, 14. 14, good. So I'm raising A to the 14 mod P. 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. Okay? 1 to the 14th power is 1. 2 to the 14th power, that's right here. 2 to the 14th power is 1. Mod 43. Does everybody see that? Yep. 3 to the 14th power is 36. Mod 43. 4 to the 13th power is 1. 5 to the 13th power is 36. 6 to the 13th power is 36. 7 to the 13th power is 6. 8 to the 13th power is 1, and so on. Okay? So this is really interesting. This is really interesting. What we're seeing is that there are 3 solutions. So these numbers 6, 36, and 1. By the way, 36 is what mod 43? Negative 7? And I guess what we're learning is that 6, is that right? Kevin is telling us something. Oh. You were going to tell us something, but you changed your mind? And Dependro, does anybody have a question? Yes. Okay. Okay. So, right, 36 is negative 7 mod 43. Let's look at, so our claim is that either one of these numbers is a perfectly good number to use for z. So we've taken, let's remember, we've taken a random number a, raised it to the p minus 1 over 3, and if it's not equal to 1, a bunch of them will be 1s. 11 over here, let's do a couple more, 8, 9, 10, 11. 11 raised to the 14th power is also 1 mod 43. A bunch of them will be 1s, but a bunch of them won't be 1s. 9 raised to the 14th power is 6, 10 raised to the 14th power is 36. Okay? And so these numbers z, so if a raised to the p minus 1 over 3, which we're calling z, is not equal to 1, then, again, z cubed is 1. And there are 3 solutions. There are 3 solutions to this cubic equation, to z cubed equals 1. In this case, those solutions are 1 itself, of course, cubed is 1, 6 cubed is 1, and the only other value is 36. And there's a very good reason for 36 to be 6 squared. Because these are the analogs of these are going to be the analogs of w and w squared. W squared is another cube root of unity. So, because when you raise 6 squared cubed, so 36 is 6 squared, and if I cube this, that's the same thing as 6 cubed squared. And so if 6 cubed is 1, congruent to 1, if 6 cubed is 1, then so is 36 cubed. Does that make sense? Thumbs up if that's good. So we had a cubic polynomial. There are 3 roots. Now, how likely is it to find such a z? How likely is it to find such a z? or such an A rather, such an A with A raised to the p minus 1 over 3 not being 1, so being either 6 or 36. What do you think? Does anybody have a guess? How many numbers, i.e., how many A mod P have A to the P minus 1 over 3 is not congruent to 1 mod P? $28. 28 is a good guess. How did you get 28, Chang? Do you want to unmute yourself and tell us why you got 28? Yes, exactly. It's exactly right. So this is 2/3 of the numbers. 2/3, I mean, not including 0. Yeah, 2/3 of the numbers. 2/3 P. I guess 2/3 of the numbers, which is 2/3 P minus 1. So, A not equal to 0. Great. Why 2/3? Well, each of these equations, y 2/3, y, so that's even better, by the way. It's even easier to find a solution to this than it was to find a solution to x squared plus y squared equals p. When we did x squared plus y squared equals p, how many numbers had, so there's something funny that happened there because we were looking at a to the p minus 1 over 2 instead of a to the p minus 1 over 4. But really what we should have been doing is looking at a to the p minus 1 over 4 and seeing that that's not 1 or negative 1. So that we get an analog of I or negative I. Well, I'll touch on that in a minute. But so the point is 2/3 of the numbers are going to be good. Why is this true? Why? Well, how many? So when p is equal to 43 and p minus 1 over 2 is equal over 3 rather over 3 is equal to 14. We're looking at the equation. So how many give us a 6? How many A's have a to the 14 minus 6 is equal to 0? Mod P. Well, it's a degree 14 polynomial, and so if the fundamental theorem of algebra were true in mod P, which it isn't exactly, but in this case it is, this will have 14 roots. So answer, 14 values of A. So we should see up in our table here, we should see 14 values of A whose 14th power is 6. So we have 7, we have 9. Do you guys still see this table? So where do we see 6s? I see, so the set of A such that A to the 14 is congruent to 6 mod 43. Does everybody see what I'm doing? Anybody have a question about what I'm about to write? Is this confusing you at all? So far so good. Okay. So which A's have a 6 here? I see A equals 7. So 7 to the 14th power is 6 mod 43. I see 9 and 13 and 14 and 15 and 17 and 18 and 25 and 26, 25 and 26, and 28 and 29 and 30, 28, 29, 30, 34, 36, 34, 36, and that's it. Does everybody see that? And how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? And the number of these is equal to 14. It's a degree 14 polynomial. We shouldn't be so surprised that it has 14 roots. So 6 is one of the values. What's the other value that's for which a to the p minus 1 over 3 is not equal to 1? So how many a have a to the 14 is congruent to the other value is 36 mod 43? What do you guys think? Can you write in the chat how many solutions we'll have to that? Yeah, Dependra sees that it's 14. Does everybody else see that we'll again have 14? Again, let's not bother to enumerate them. We will have 14 such values of A. So total, 14 plus 14 is 28 values out of the total number of values, which is one less than the prime. So there are 28 values out of 42, so 2/3, right? This fraction is 2/3, so 2/3 of the values of the A's have a to the p minus 1 over 3 is equal to 6 or 36. In other words, is not equal to 1. So we have a really good chance. So when we calculate a to the p minus 1 over 3, we always see 3 types of values. Yes, because we can't see more than 3 types of values, because the polynomial z cubed is congruent to 1 can have at most 3 roots. So this polynomial has at most 3 roots. In this case, it has exactly 3 roots. And those are the 3 values that we're seeing here. So when we calculate a to the 14, we're always getting something that when we cube that something, we'll get 1 from Fermat's little theorem. Does this kind of make sense? We're going to do some more examples in a minute, so maybe it'll make more sense after that. Okay. So once we have such a z, we have such a z. So what should we take in this case? Do you want to take 6 or 36? 6, good. I agree. Sheik, you also want to take 6? You were going to write something? No, okay. So let's take z equals 6. We know that z cubed minus 1 is congruent to 0 mod p. Right? This is going to be the same argument. We're just running the same argument again. What does that mean? That implies z cubed minus 1 as an integer is equal to p times k as an integer for some integer k. So what is it in this case? In this case, in our example, z cubed 6 times 36 times 6. What's 36 times 6? 2. Does anybody know? 6 cubed. 216, good, very good. 216, so minus 1 is 215. And 215 has to be 43 times something. What's 215 divided by 43? I'm going to guess 5, because we got to get a 5 in there. All right? So far, so good? So this would be k. But check this out. What do we know about the polynomial z cubed minus 1? This factors. This factors as over the Eisenstein integers, it factors completely. So over z adjoin w, the polynomial z cubed minus 1, well, over the integers, this factors as z minus 1 times z squared plus z plus 1. But over the Eisenstein integers, this factors even further. The z minus 1 is already there, and this has two roots, omega and omega bar. Right? So let's look at this. Let's look at our example here. So 6 cubed minus 1 has to factor, 6 cubed minus 1 has to factor as 6 minus 1 times 6 squared plus 6 plus 1. And 6 minus 1 is 5. And this is 36 plus 6, 42 plus 1 is 43. 5 times 43. There's our factorization. Does everybody see that? So this is all in our example. In general, what we see is that z cubed minus 1, which factors as z minus 1 times z minus the cube root of unity times z minus omega bar, is equal to p times k. So this is an equation in the Eisenstein integers. So far, so good? Now, can z minus 1 and p have a factor in common? That we could already see at the level of integers. So before we went to the Eisenstein integers, in z, z minus 1 times z squared plus z plus 1 is equal to p times k. And z is not 1 mod p, is not congruent to 1 mod p. And in z, p is a prime. And in z, p is prime. So since z is coprime to p, that means z minus 1 divides k. And what that means is, in this equation, z minus 1 times z squared plus z plus 1 is equal to p times k. We can divide, so let's say k is equal to z minus 1 times, I don't know, L. So we can divide both sides by z minus 1. So if I divide by z minus 1 here and here, what I'm left with is z squared plus z plus 1 is equal to p times L. Does everybody see that? What's L in our example? In our running example up here? Can you write your answer in the chat? Let's see if this is making sense. K is 5. K is 5 in our example. Z is 6. So L is P is 43. Keep going, Sheik. Keep going. P is 43. Z is 6 in our example. And K was 5. Because that was the 5 times K times P is Z cubed minus 1. So what's the leftover? 5 is 6 minus 1 times 1. Right, 3. Right, so in our example, L is just 1 and there's nothing left over, but pretend there was something left over. Okay? So this is an equation in the integers. This is still in Z. But now we lift this in Z adjoin omega. What we see is that Z minus omega times Z plus, not Z plus omega, Z minus omega bar is equal to P times L. Now, does P divide either of these? Does P divide Z minus omega or P divide Z minus omega bar? Why not, Dipendro? You can unmute yourself if it helps. I guess we don't need this screen anymore, right? This Mathematica file. So let's close that. It doesn't seem to. Okay. So what would it mean that P divides one of these? It means if it did, if P divides Z minus W, then P times something, then Z minus W is something. Let's call it A plus B. I don't want to use A. Whatever. C plus D W times P. But P is itself real. So this will just be P times C plus P times D W. So P times D has to equal -1. So P times C is Z. That might be. But P times D has to equal -1. And D is a whole number. D is an integer. Okay, so there's no... So the answer is... P does not divide Z minus W, because this is, like in the lattice, this is at height 1. Or root 3 over 2. But the W component is 1. So P can't divide this, and P can't divide this either. Does that make sense? Can I get a thumbs up if everybody is following that? So the fact that P doesn't divide either of these, and yet it divides the product, but P divides the product of Z minus omega and Z minus omega bar. So that means P is no longer prime. P is not, so P is not prime. And so it has a decomposition. And whatever that decomposition is, it's going to have a GCD. So if P is equal to, I'm running out of letters. Well, let's just keep it C. Oh, X and Y. X plus YW times X minus YW, which, by the way, would be exactly the representation that we're looking for of P as a value of this quadratic form. Then these components are irreducible. They have to have a GCD in common. They have to divide. So the components, let's say X plus WY, must divide at least one of Z minus W or Z minus W bar. Does that make sense? Sheik is writing something. So P times D is 1 is a contradiction, right? Right. Because D is an integer, and P can't divide, P is a prime. Exactly, that's the contradiction. Daniel, you want to say something? Yes, thank you very much. That is, of course, a W bar. Thanks. Yes, Daniel and Devendra, thanks for catching that. Okay? So all that's left, so what's left? Now how do we get, we don't have these components, but we can take, how do we pull out a component? Something very similar to what we did for the case of sums of two squares and the Gaussian integers. So last step, let's see, did we have a step 2 or we only had a step 1? Step 1 is find a z, and step 2, last step, also known as step 2, is can you lower your hands and then raise your hand if you think you know what the last step is going to be? Once you have this P and you have a Z minus omega, what are you going to do with them? What did we do once we found Z plus I and T in the Gaussian integers? Karen, you have a thumbs up? Or is that just a... Dependra, you have your hand up. Oh, no, meant to be a thumbs up. Chang? Yes, we find the GCD. Last step is to take the GCD in the Eisenstein integers, the Eisenstein integer GCD algorithm, of what two numbers? Chang? Yes, perfect. P and Z minus omega. All right, so let's do it. Let's do it. In our example, so we want the GCD of P. P was 43, and Z minus omega. Z was 6. 6 minus omega. Okay, so let's compute this GCD. You guys want 3 minutes to do it on your own, or you want to do it all together? Can you write in the chat all together or on my own? Give me 5 minutes to do it. All right, the votes are all to do it together. Well, let's start it together. Okay, so what's the GCD algorithm? Let's recall how that works. The GCD algorithm. So remember, what we're going to do is write n as qm plus r, and the way we do, so recall, division algorithm, n over m will be close to a Gaussian integer z adjoint omega. That's how this works. Okay, so in our case, for us, we're looking at 43 is equal to q times 6 minus omega plus r. So we want to look at 43 divided by 6 minus omega. And how do we, so this is n over m. Does that make sense? Thumbs up if this is good. Great. A couple of thumbs up are coming in. Okay, and how do we do this? How do we figure out what this is? Yep, multiply the top and bottom by the conjugate, 6 minus omega conjugate, 6 minus omega conjugate. So on top I get 43 times 6 minus omega bar. And on bottom, I get, so this is 36. I have a minus 6 omega. I have a minus 6 omega bar. And a plus omega omega bar, which is 1. So far, so good? So this is minus 6 omega plus omega bar. Let's remember what omega plus omega bar is. Omega is here. Omega bar is here. So omega plus omega bar is that point. And what's the x part here? What's this distance? Oh, I'm asking what the so we're going to get this parallelogram thingy, and I'm saying what's the x coordinate, because the imaginary parts are going to cancel out, and we're going to get some real point, and it's going to be twice whatever this distance was, because that's how the vectors will add up. Yes, exactly. This distance is a half. This distance is a half. In other words, w omega is a half plus root 3I over 2. So this one, well, negative a half actually. So this distance is a half, which means that distance is a half, which actually this point isn't here, it's here. So all I'm saying is that w plus w bar is actually negative 1. So this is negative 6 times w plus w bar, which is a positive 6, because w plus w bar is negative 1. Actually, we knew that from the very beginning because because the way we got this was that z minus omega times z minus omega bar is z squared plus z plus 1. So this is z squared plus z plus 1. So actually we had much less work to do if we remembered what this conjugation did to the original z. But okay, so what is 36 plus 6 plus 1? You can write it in the chat. So my numerator is 43 times 6 minus omega bar. My denominator is 36. This is a plus 6 minus 1. Because there was a minus 6 times negative 1. 36 plus 6, 42, plus 1. So Q is exactly Q is equal to 6 minus omega, and R, what's the remainder? Can everybody write in the chat what the remainder is? Yes, Sheik, excellent. The remainder is 0. That means the previous, once we hit remainder 0, the previous value of, well, there was no previous value of remainders, but the previous m, that means m is the GCD, which means 6 plus omega is the GCD. I guess 6 minus omega. M was 6 minus omega. 6 minus omega is the GCD of 43 and 6 minus omega. So maybe this is not a good example because when we got the number 6, we immediately had a representation of 43 all the way back here. All the way back here, we immediately had a representation of 43 as x squared minus xy plus y squared. So 43 is equal to x squared minus xy plus y squared, where x and y are equal to, what should x be? 6, and y is, so now I have 6 squared minus 6 times something plus 1 squared, so y is, Sarah, so if I put 1, then I get 36 minus 6 plus 1, so I have to put a minus 1 here. So this is 6 plus, so this is, if I write this as x plus y omega times x minus, or x plus y omega bar, then y is negative 1. Does that make sense? So that's it. Well, that was cheating, because we basically had it from the very beginning, because we saw that 6 squared plus 6 plus 1 was 43. So let's do a harder one. Any questions on solving this problem for the prime 43 before we do a harder prime? We're all good to go? We should do a harder prime? Any questions, comments, criticisms, concerns? All right, let's do a harder prime. Somebody gave us a harder prime before. Was it 97? Let me share this screen again. Okay, you guys can see the screen? So let's do p equals 97. So 97 is a prime, it is 1 mod 3, and let's get that same table. And now check out these values. Okay, new example. The prime 97. For the prime 97, I'm looking at p minus 1 over 3. P minus 1 over 3 is, you want to write it in the chat? Yeah, subtract 1, 96, divided by 3, 32. 32. So now I'm making a table of a versus a to the 32 mod 97. So here's 1, 2, 3, 4, etc. 1 to the 32 is always 1, but 2 to the 32 is 35. And 3 is also 35, and 4 is 61, and so on. And how many numbers, so here's a test of your understanding. How many a mod p, and the non-zero ones, have a to the 32 is congruent to 35 mod 97. How many of these a's how many 35s will I see in the table? Everybody see that? So we'll get, exactly, so the answer is that we'll get 32 a's with a to the 32 equals 35. And how many a's with a to the 32 being equivalent to 61 mod 97? How many 61s will we see in this table? Another 32? Yep. Again 32. So total number of a's with a to the 32 not equal to 1, in other words, their only options other than 1 are 35 and 61. The total number of a's is 64, which is 2/3 of 96. And 96 is p minus 1. This is 2/3 of p minus 1. Okay? So if we just start guessing a's at random, we have an extremely good shot You know, the first time you guess a random A, you have a 66% chance of finding an A which raised to the p minus 1 over 3 does not give you 1. And then you're golden. Okay? So which A should we take? How about A equals, you want to take A equals 2? Well, it doesn't matter. It doesn't matter which A we take. So, step 1, find whatever A you want such that A to the p minus 1 over 3 is not 1. Let's say A equals 2, 3, 4. What do you guys like? 2. Perfect. Thank you, Sheik. A equals 2. And then set Z to be A to the p minus 1 over 3. So in the case of 2, if you still see that, in the case of 2, A to the 32 is 35. So Z in our case is 35. Okay. So what does that mean? Then Z cubed is congruent to 1 mod P. That means, so that was step 1. That means that Z minus 1 times Z squared plus Z plus 1 is equal to P times some integer. Right? Because Z cubed minus 1 is 0 mod P. And Z cubed minus 1 factors, so this is Z cubed minus 1. Factors as this. Okay? What is Z minus 1 in our case? Z is 35, Z minus 1 is 34. P is 97. And let's figure out what K is. So Z cubed, Z is 35. Z cubed, 35 cubed is this giant number. This giant number is 42875, whatever it is. That number divided by 97, so Z cubed divided by 97, is not divisible by 97 because we didn't subtract 1. Oh, I didn't subtract 1 here, so this is a 4 instead of a 5. If I subtract 1, does everybody see that? Divide by 97, so K in this case is 442. And the point is 34 is co-prime with 97, so 34 has to go into the 442. So we can get rid of this 34 by dividing on both sides. So divide out Z minus 1 from the left-hand side and K on the right-hand side. Since in the integers it's not going to touch the prime P. Can I get a thumbs up if you're following? Great. Great. Okay, so we're going to divide out this 34. So what we now have is Z squared plus Z plus 1, where Z is 35, is equal to 97 times, what's 442 divided by 34? 13. Okay? So this is still an equation in the integers. We took an equation, this is an equation in Z mod P. This is in Z mod P. We raised it to an equation in the integers, and now we're going to raise it to an equation in what am I going to do with this Z squared plus Z plus 1? I'll factor it as Yep. So now we lift this equation to an equation in this Eisenstein integers ring, z minus omega times z minus omega bar is 97 times 13. So step 2 will be, what is step 2? Compute the GCD. Find the GCD, which will not be as simple at this time, of the prime 97, and z minus omega, z is 35. 35 minus omega. Okay, you guys ready to do it? Now do you want 5 minutes to try to do it by yourself? Or all together? Why don't you write in the chat? What's the vote? Ray says all together. All right, let's do it all together. So I'm going to do it all together, but maybe a little bit slowly so that if someone wants to do it on their own, they can do it on their own and not listen to me. So again, we're going to start with solving this equation. So we're writing 97 as q times 35 minus w plus r. And the way to figure this out is to look at 97 divided by 35 minus omega. So I multiply top and bottom by 35 minus omega bar. Now 35 minus omega, we already know what the norm of 35 minus omega is because it's z squared plus z plus 1. Actually, we don't know, do we? But we know that it's going to be 35 squared plus 35 plus 1. Well, I don't know what that is. 35 squared plus 35 plus 1 is 1261, in case you were curious. So that's the denominator, 1261. How about the numerator? 97 times 35 is 3395. 3395 minus 97 omega bar. Okay? So on top I have 3395 minus 97 omega bar. And what do you want to call that near? This looks to me like the real part is near very roughly 2. Yeah, 2 will get us to 24. Maybe 3 gets us a little closer, because 3 gets us like to 36. You want to try? It doesn't really matter which one you do. I'm going to say 3 in the real part, and how about in the imaginary part? 97 over, or in the omega part, 97 over 1261. 97 over 1261 is going to be pretty close to 0. Yeah, exactly. Good. So just 3. So let's make q equal to 3. Okay? So then we go back into this equation. So 97 is equal to 3 times 35 minus omega plus r. So r is equal to 97 minus 3 times 35 is negative 8. So if I move this to the other side, I get negative 8 plus 3 omega. Is everyone getting that same first remainder? Great. So this was remainder 1 and quotient 1. What do I do next? Next I'm going to divide two numbers. What two numbers? You remember the Euclidean algorithm? Right. I have this 33 35 minus w, which was the previous remainder, even though it wasn't a remainder, it was what we started with, 35 minus w, and I'm going to divide that by this thing, negative 8 plus 3w. Does everybody see that? So let's look at that quotient. So 35 minus w over negative 8 plus 3w. Gosh, this is going to get messy. Negative 8 plus 3w bar. And a negative 8 plus 3w bar. Now, thankfully, we know what the norm is. The norm, remember, the norm of x plus y omega is x squared minus xy plus y squared. So the denominators are not so bad to work out. X squared is 64, because that's 8 squared, minus x times y plus y squared. Does everybody see how I did that? This is just the norm, because we multiplied by the conjugate. And the norm, we already know what that is. Am I losing people? Give me a thumbs down if I've lost you. And give me a thumbs up if you're keeping up with the computation. Good. Awesome. Thanks, Sheik. All right. And let's do this part. So I have negative 8 times 35. Gosh. 8 times 35 is 280. So I have a negative 280. Negative 280. This is going to get a little messy. 3 times 35 omega bar. Now, let's see. Omega bar, is there a nice way to write omega bar? There kind of is and there kind of isn't. Let's just, well, how do I want to say this? Let's leave it as omega bar. Omega bar is the same as omega squared. Yeah, we want to be regularly using the fact that, so here's omega. Omega bar is omega squared, but remember that omega satisfies the equation omega squared plus omega plus 1 equals 0, because that's the factorization of omega cubed minus 1 equals 0. So omega bar is exactly negative omega minus 1. Yeah, exactly. Exactly. So anytime we see omega bar, it's better to put negative omega minus 1. But all right, 3 times 35, we could probably do that in our heads, but let's not. So I have plus 105 times omega bar. So I'm doing this term now. Omega bar is negative omega minus 1. Then it's easy. Negative omega times negative 8 plus 8 omega. And then negative omega omega bar times 3. What's this last term? Yep. Everybody see that? Alex is writing something. Sheik is writing something. Did you guys also get negative 3? I'm just making sure. Great. All right. So we still have to work out what this denominator is. How about the numerator? I have negative 280 minus 105 minus 3. That's a negative 388. Can anyone verify that that's correct? And then what's the omega part? I have a negative 105 plus 8. So I have negative 97 omega. Did everybody get that for their numerator? Okay, and the denominator, I need 64 plus 8 times 3 is 24 plus 9. Not so bad. Hey, we got 97. That's cool. Wait a second. This is kind of cool. This is kind of cool. What's 388 over 97? 388 over 97. I have a feeling we're in luck. This is negative 4. This is exactly equal to, not approximately equal to. Yeah, exactly. It's 4. With a minus sign is negative 4. negative 4 minus omega, that's Q2. So what's R2? What's the remainder? 0. Everybody see that? So what's the GCD? So the GCD of 97 and 35 minus omega is R1. And R1 is right here, is negative 8 plus 3 omega. Which means negative 8 plus 3 omega divides 97. So we have expressed, so we're done. So 97 is x squared minus xy plus y squared, which is the norm of x plus omega y, where x and y are equal to, it's right here. This thing divides 97. So x is do you guys see? So tell me what x and y are. Karen. Thank you. It's just, you just read it off of here. Negative 8, right? X plus y omega is negative 8 plus 3 omega. So x is negative 8 and y is 3. And negative 8 squared is 64. I mean, this is exactly the calculation we did up here. Negative 8 squared is 64. Negative 8 times 3 is negative 8 times 3 is plus 24. 64 plus 24, 88, plus y squared plus 9, 88 plus 9, 97. So we have expressed 97 as the norm of an Eisenstein integer. Cool? And this method is extremely fast. There are only 2 steps. Step 1, guess at random until you find something that works. And step 2, take the GCD. Daddy's busy now, sweetheart. Thank you.
I just want to play longer than
Okay, does that make sense? Can I get a thumbs up if that's good or not good? Since I'm getting bonked on the head. Thumbs up. All right. Should we recap? So let's recap. Recap. To solve, P is equal to the norm of x plus omega y. Eli, Daddy's gonna have to remove you. Please close the door behind you. Thank you. X squared minus xy plus y squared. Step 1, drop down to go to z mod p and find a such that a to the p minus 1 over 3 is not 1. You have a 66% chance. Every time you try to find such an a at random, you have a 63 chance, 66% chance, 2/3 chance of finding such an a, and set z to be that number, a to the p minus 1 over 3. I mean, of course, mod p. You don't want to do this in actual numbers. 35 to the whatever it was, 32 is going to be some god-awful number. You only want that mod p. It wasn't 35, it was 2 raised to the 32. We don't want that either. We only want it mod 97. And once we do that, then step 2 is compute the GCD in z adjoint omega of the prime and z minus omega. And whatever this is, if this is x plus y omega, then we're done. Then x squared minus xy plus y squared is exactly equal to p. Any questions about that? All right, so let me preempt what we're going to do next. So next set of ideas is this game. This worked great for the norm forms, x squared plus y squared and x squared minus xy plus y squared. We kind of very quickly were able to find representations of primes. Once you find a representation of one prime, how do you find representations of products of primes? Yeah, I guess I didn't finish this. Once you know how to do this for a single prime, how do you find, okay, before the next set of ideas, we have 2 minutes left. So we know that, what was it, 37 is, what did we get when we did 37? What were the two numbers? 6 and negative 1? So this is 6 minus omega times 6 minus omega bar, right? And we know, and 97 is negative 8 plus 3 omega times negative 8 plus 3 omega bar, right? We know these two things. So what do we do? What if n is 37 times 97? How do we handle products of these? 37 times 97 is this big number, 3589. Can we find a representation of this as, can we find x and y such that 3589 is equal to x squared minus xy plus y squared? Yes, exactly. Take the product of the two corresponding Eisenstein integers. This is 37 times 97, but 37 is 6 minus omega times 6 minus omega bar, and 97 is negative 8 plus 3 omega times negative 8 plus 3 omega bar. So just multiply these two Eisenstein integers and then take the bar. And that'll give you a representation of 3589 as this, in terms of this norm form. So what is 6 minus omega times negative 8 plus 3 omega? This is not hard. So I get a negative 48. I get a plus 18 omega and a plus 8 omega. So 18 omega plus 8 omega. Am I doing this right? 18 plus 8, 24. No, 26 omega. And then a minus 3 omega squared. But what is omega squared? Omega squared, again, if you remember, omega squared is down here, and it's negative 1 minus omega, if this is omega. So minus omega is over here, and that minus 1 gives me omega squared. This is a little aside. So this is minus 1 minus omega. So what do I get here? Negative 3 times negative 1 is positive 3, so I get negative 45 plus negative 26 plus 3, sorry, 26 plus 3 is 29 omega. So we've learned that this thing divides 3589. And let's check if 45 squared minus 45, I guess plus 45 times 29 plus 29 squared, which is this value, so x squared minus xy plus y squared. If this is x and this is y, what is 45 squared plus 29 times 45 plus 29 squared? Uh-oh. Did I get the sign wrong? Did anybody check my my arithmetic? Let's see. We're multiplying these two. 6 times negative 8, negative 48. What did I do wrong? Daniel, you see my mistake? Oh, 43. Of course. What am I doing here? 37. Where did I get 37? This is 43. Thank you. 43. 43, not 37. That's what I did wrong. I just can't copy. What's 43 times 97? 4171. Beautiful. 4171, which is exactly the number we wanted. So this is 4171 and 4171. Okay, so the way to find a general number, which is a product of primes that are 1 mod 3, is to do this very efficient algorithm for each one, and then take the products of the Eisenstein integers. Let me write that down. So for general n, which is a product of primes, each p is 1 mod 3, otherwise there is no representation, just multiply, just find representation of each, and multiply those Eisenstein integers. Multiply Eisenstein integers. Okay, does that make sense? So just foreshadowing very little, we're going to look at what happens for general quadratic forms, and all this beautiful stuff no longer is applicable, but there's still a whole other beautiful story that we will get to